Question number 4. Let P be the set of all triangles in a plane. So we have drawn some triangles and R is the relation defined on P as ARB if A is similar to B. So these are the similar triangles which we have drawn. Similar triangles will not be of same size, but the sides will be proportional. First side, first side, first side, second, 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 third and third and third. So they will be proportional. We want to show R is an equivalence relation. We know every triangle is similar to itself. So we will say A related to A or R is reflexive. Suppose A is similar to B, then I can immediately say B is also similar to A. So A related to B implies B related to A. Yes, triangle A is similar to triangle B, or we'll write in words triangle B implies triangle B is also similar to triangle A. So we can declare R is symmetric. The next idea is transitive. What do you mean by transitive? A related to B and B related to A implies, B related to C implies A related to C. See, this triangle is similar to this triangle and this triangle is similar to this triangle implies A is similar to C. So this is obviously true. So I can say triangle A similar to triangle B. Triangle B similar to triangle C. So this is AND implies triangle A is similar to triangle C. Therefore, R is transitive. So writing this is difficult. You can write in sentences. Triangle A similar to triangle B. Triangle B similar to triangle C implies triangle A is similar to triangle C and therefore R is transitive, and hence I can declare R is an equivalence relation. Why? R satisfies all the three: reflexive, symmetric and transitive. Therefore R is an equivalence relation, and that's the answer. Question number 5. Set of natural numbers. The relation R is defined as ARB if 2A plus 3B equals 30. Now let us find out which pairs AB will be suitable to obey this relation. So first I want to show A, B belong to N. 2A plus 3B equals to 30. From here, what is 2A? 30 minus 3B. And what is A? 30 minus 3B divided by 2. I told you, whenever we are in relation problems, the set is very important. It's a natural number. So fraction not allowed. If A is a natural number, the numerator should be a multiple of 2. Then only I can cancel and A can be a natural number. So B cannot be odd numbers. B I have to put only even numbers. So let me put B is equal to 2. If I put B is equal to 2, A equals 30 minus 3 into 2 by 2. 30 minus 6 by 2. 24 by 2, which is 12. B equal to next even number 4. A equal to 30 minus 3 into 4 by 2 or simplify the answer, which is 9. Put B is equal to 6. A is 30 minus 3 into 6 by 2, that is 30 minus 18 by 2, which is 6. Put B equals to 8. 30 minus 3 into 8 by 2, which is 6 by 2, that is 3. Can I put B is equal to 10? If I put B is 10, 30 minus 3 into 10, 30. 30 minus 30 will become 0. 0 is not a natural number. So B equals to 10 is not suitable. We shall tabulate A value and B value. My question is A related to B. So A related to B only is given. Implies what all I have in the set? A value 12, B value 2. First pair. A value 9, B value 4. Second pair. Third pair. A value 6, B value 6. And A value 3, B value 8. Having this pairs, I want to check. So we have listed the pairs. We want to check whether it is reflexive, symmetric, transitive and equivalence relation. So let us see. 12, 12 is present. What do you mean by reflexive? That number should come with that number itself. A or A implies it is reflexive. But here 12, 12 is not in the set. So 12, 12 is not in the set, implies it is not reflexive. So we say R is not reflexive. The second idea, A or B implies B or A, then we call it is symmetric. But in this problem, 12, 2 belongs to R. Does not imply 2, 12 belongs to R. See, we have only 12, 2. We do not have 2, 12. So we will say R is not symmetric. The next idea, transitive. A or B and B or C implies A or C, then R is transitive. Check in this problem whether it comes correctly. A or B, 12, 2. I must check 2 to some number, but 2 to there is no combination. 9, 4, 4 to there is no combination. 6, 6, 6 to anything else, no combination. 3, 8, 8 to also. So I told you only whenever these two are there, I must check this idea. But these two, there is no such combination. Therefore, R is transitive only. There is nothing I can show doesn't belong all that. So, R is transitive. But it is not symmetric and not reflexive. Therefore, R is not an equivalence relation. Let us remember, a relation is equivalence only when it is reflexive, symmetric and transitive. Even if one idea fails, I will immediately declare it is not an equivalence relation. Question number 3. A is a set containing A, B, C, 3 elements. R is a relation defined as AA, BB, AC. Obviously, we can check R is not reflexive, symmetric or transitive. The question is, write down the minimum number of ordered pairs to be included in R to make it reflexive, symmetric, transitive and equivalence relation. What is A given? A, B, C. If it needs to be reflexive, what all should be there? the repeated pairs AA, BB, CC should be in R to be reflexive. Check which is all present in R. AA, BB are present. Which is not present? CC. Therefore, include C, C to make R reflexive. So the question is include what? So include C, C. Already AA, BB are there. So I must include CC to make it reflexive. The second idea is symmetric. Symmetric implies A, B belongs to R implies B, A belongs to R. Check in the question now. A, A. The reverse A, A is present. B, B. The reverse B, B is present. What is the third one? A, C. What is the reverse? C, A. So, A, C belongs to R should imply C, A should belong to R. So, include what? Include. Because A, C is there, I have to include C, A into R to make R symmetric. What is the third question? Transitive. So, transitive, what is the formula? Whenever A, B belongs to R and B, C belongs to R implies A, C belongs to R. There are only three here. Check it. A, there is no other A here. AC. If I join these two, AC, it's already there. BB, there is no B connecting at all here. So, AC and there is no C connecting. So, I am left with BB, AC itself transitive. So, I will say nothing to include. So, for transitive, I need not include anything. It is already transitive only. R is transitive. The last idea, I want to say what all should I include for R to be an equivalence relation. So, what all I must include? All that is in the subheadings. So, include. Reflexive means I must include CC. Symmetric, I must include CA. Transitive, nothing to include. So, I have to include CC and CA to make R to be an equivalence relation. That is the question. We need to check what all I must include. Minimum number of pairs, not maximum. So, R is an equivalence relation if I include CC and CA with a given set. That is the problem. Question number 6. Prove that friendship is not an equivalence relation in the people of Chennai. So, the set given is people of Chennai. Reflexive. We can say, are you a friend of yourself? Yes or no? A is a friend of A. That is true. Everyone should be a friend of your own selves. So, A is a friend of A is true. So, I will say A related to A implies R is reflexive. The second idea, check whether R is symmetric. Take two friends. A is a friend of B implies B is a friend of A. So, A is a friend of B implies B is a friend of A. So, I can say A is related to B implies B is related to A. Therefore, R is symmetric. What is the next idea? Transitive. See, you may have a friend in 10th standard. So, A is a friend of B and your friend may have another friend in 10th standard. So A is a friend of B and B is a friend of A. Here we take C. So A is a friend of B and B is a friend of C. This friend may be in 10th standard friend and this friend may be a new friend in 11th standard. Doesn't mean these two need to know each other. Or else I can say A is a friend of B. This is in your neighborhood. B is a friend of C. This is in school. So A and C need not be friends. So I say A is a friend of B and B is a friend of C does not imply A is a friend of C. Therefore, A related to B and B related to C does not imply A related to C. R is not transitive. So friendship, we could say it is reflexive and symmetric, but friendship need not be transitive. This friend A need not be a friend of C. Sometimes they may be friends, but every time it is not the case. So R is not transitive and I will declare R is not an equivalence relation. In this problem, R represents friendship. So friendship is not an equivalence relation. Question number 7. The set is set of natural numbers. A is related to B if A plus B less than or equal to 6. We need to list the pairs and we have to check whether it is reflexive, symmetric and transitive. So what is the condition given? A plus B less than or equal to 6. Tell me which are the pairs that give me less than or equal to 6. Natural number start from 1 onwards. So I will say 1, 1. 1 plus 1 is below 6. 1, 2. 1 plus 2 is below 6. 1, 3. 1 plus 3, 4 below 6. Same way tell me 1, 4. 1, 5 also will come. 1, 6 can I say? 1 plus 6 will give me 7. But I want below or equal to 6. So all one combination I finished. Start with 2 now. Tell me the numbers. 2, 1. 3 is less than 6. 2, 2. 2, 3. 2, 4. Can I say 2, 5? No. 2, 5 will give me 7, which is more than 6. So tell me with 3 now. 3, 1, 3, 2 and 3, 3 equal to 6 is done. Next idea, 4, 1, 4, 2. That's all. 4, 3 will give me 7. So I want 6 or below. The next idea, 5, 1. Can I say 5, 2 and all? No. Can I start from 6? 6, 1 itself is more than 6. So these are the ordered pairs which will satisfy the condition A plus B is less or equal to 6. Now check whether it is reflexive. See 1, 1 is there. Check whether 2, 2 is there because 2, 3, 4 and all coming here. 2, 2 is there. 3, 3 is there. 4, 4 is not there. So even if I find one answer, 4, 4 does not belong to R. Implies R is not reflexive. So whenever I want to say it is not, I am expected to give one example. So 4, 4 is not in R. I can immediately say it is not reflexive. Symmetric idea. In symmetric, check 1, 1, okay. The reverse check. 1, 2 is there, 2, 1 is there. 1, 3 is there, 3, 1 is there. So from the given ordered pairs, 2, 4 is present, 4, 2 is present. So I am able to say whenever A, B belongs to R, B comma A also belongs to R. So A related to B implies B related to A. This is, obviously I can say it is true from R. Therefore, R is symmetric. What about transitive? Transitive, what I want to show? A related to B and B related to C implies A related to C. Even if I say one example that does not come up to this relation, I will say it is wrong. For example, let me take with big numbers, say 4 or 5, let me take. 1 comma 4 is there. 4 comma 2 is there. So if I take 4 comma 1, 1 comma 4, these are in R. 4 comma 1 is in R. 1 comma 4 is in R. The combination, what will I say? 1, 1 if I hide. 4 comma 4 should belong to R. But 4 comma 4 does not belong to R. See, 4, 1, 1, 4 is present. The combination 1, 1 if I cancel, 4, 4 should come. 4, 4 is not in R. Therefore, R is not transitive. So, this particular relation I am checking and I have confirmed it is not reflexive, not transitive, but it is only symmetric. Therefore, R is not an equivalence relation, because equivalence relation implies it must satisfy everything: reflexive, symmetric, transitive. Even if one fails, I will immediately say R is not an equivalence relation, and that's the answer. Question number 9. The set of all integers. What do you mean by integers? Z we denote, and integers imply +1, -1, +2, -2, 0. So all the positive and negative numbers. And the relation is defined as m minus n is divisible by 7. What do you mean by divisible by 7? Say 0. All the 7 multiples I have to say 14, 21, 28 and so on are divisible by 7. Is only positive numbers? No. Even negative numbers are divisible by 7. So let me check. M minus n means now I have to put m minus m. What is my answer? 0. 0 is divisible by 7. So I will say m minus m is 0. 0 is divisible by 7. Therefore, m is related to m implies R is reflexive. The second idea, symmetric. Whenever m minus n is divisible by 7, n minus m is also divisible by 7, isn't it? Whenever plus 14 is divisible by 7, minus 14 is also divisible by 7. Therefore, I can say whenever m is related to n, I can also say n is related to m. m related to n implies n related to m. Therefore, R is symmetric. The next idea I want to say transitive. M minus n is divisible by 7. N minus say some other letter P. N minus P is divisible by 7. Implies the subtraction m minus n is divisible by 7. N minus p is divisible by 7. I want to show m minus p is also divisible by 7. So I can declare it is an equivalence relation. Now some of you may have a doubt. Check it with an example. Take some divisibility numbers for 7. plus or minus 14, plus or minus 21, plus or minus 28 and so on. So these are numbers divisible by 7. Or I will say this is 2 times 7, 3 times 7, 4 times 7. So divisible by 7 implies it is a multiple of 7. So m minus n divisible by 7 says m minus n is equal to 7 into k1, some constant. 2 times 3 times we said. Similarly, k1 is some number. This implies m equals n plus 7k1. Now what is the second idea? N minus p. This is also divisible by 7 we said. Put some other constant, say 7k2. So this tells me p is equal to, let me say minus p. Bring n to this side. Minus n plus 7k2. Because I want m minus p. So from here I found out m. From here I found out minus p. Now add it, m minus p equals, n and n will get cancelled, 7 is common, k1 plus k2. So 7 into some constants. So I will decide m minus p is divisible by 7. That is what we have written. So we can conclude m related to n and n related to p implies m related to p implies r is transitive. Since we have shown r is reflexive, symmetric and transitive, I can decide r is an equivalence relation, and that's the problem. So this transitive idea, some of you may have a doubt. We'll see this again. M minus n divisible by 7 implies m minus n is 7 into some constant. Put the constant as k1. N minus p divisible by 7 says n minus p is 7 times some constant. I want m minus p. So from here m is minus n goes to the other side as plus n. I want minus p. So from here minus p is 7k2 minus n. As I add m minus p, plus n minus n cancels, 7 is common, k1 plus k2. So I get m minus p 7 into some constant. Therefore, it is divisible by 7. And so, I can declare R is transitive. Since it is reflexive, symmetric and transitive, we can declare it is an equivalence relation. Question number 8. Given set A contains A, B, C. Find equivalence relation on A with the smallest cardinality and with the largest cardinality. It's a simple problem. To recall the introductory part, whenever I want smallest cardinality, write the ordered pairs having same elements. Say A is an element means write A comma A. B is an element implies B comma B. C is an element implies C comma C. So this will be an equivalence relation. So always remember, with all the letters, all the elements given in A, let me write the ordered pairs repeated like this. AA, BB, CC. This is a new relation that I write, and this relation is an equivalence relation. Check whether it is correct. So this is of the smallest cardinality I can say. So let me call this as R1. So R1 has only 3 elements. When A has 3 elements, the smallest cardinality is also having only 3 elements. So I will say this is the smallest cardinality. Check whether it is equivalence relation. AA, BB, CC. It is reflexive. Whenever AA is there, the reverse AA, BB, reverse is also BB, CC, the reverse is also CC. It is symmetric. and AA, no connecting elements at all to check transitivity. So transitivity should be checked only if connecting element is there. A, there is no connecting with A at all. So it is always transitive. And so I can declare it is an equivalence relation. So this R1 is reflexive, symmetric and transitive. And the smallest cardinality, if they give you 3 elements, the smallest cardinality also will contain only 3 elements, and that is the repetition pair. The next idea is largest cardinality. You will write the universal relation. So largest cardinality implies it should be the universal relation. What do you mean by the universal relation? The universal relation is nothing but A cross A. So what is A cross A? All the ordered pairs. A is the first element, AA, AB, AC. Then I must write with B. BA, BB, BC. Then I must write with C. CA, CB, CC. So we are able to write, there are 3 means 3 into 3. 9 pairs will come and that will create A cross A, the largest cardinality on A, which is the universal relation, and this I can call R2. R2 is an equivalence relation. Why do I say that? Check whether it is correct. All the repeated pairs are there. AA, BB, CC. So all are there. So R2 is reflexive. Whenever AB is there, BA is there. Whenever AC is there, CA is there. Whenever BC is there, CB is there. So I will say it is also symmetric. Finally, I come to transitive. AB and BA combine. BB cancel means AA is present. AC and CB. CC cancel means AB is present. So I can say it is also transitive. So R2 is reflexive, symmetric, transitive. I can declare R2 is an equivalence relation. So the smallest cardinality, just write the repeated pairs. Largest cardinality, just write the entire relation. That is a universal relation I am writing. That will be the largest cardinality. A, B, C, we write like this, the pairs. A, B, C. For this also A, B, C. So 3, 3, 3, totally 9 pairs will come, which will create equivalence relation on R with the largest cardinality.